Hey chemists, how you going? Just want to talk you through this back titration problem through essentials, and we'll just kind of work through it together. So first of all, hopefully you've seen my explanation of a back titration from the previous video, but we'll go through it again, okay? So essentially, a back titration is a two-stage analytical technique where a known amount of an excess of one reagent is added to a reagent of unknown concentration. So in this instance, for chemical reaction 1, this is kind of like your regular titration. So you've got reactant A and you've got reactant B, okay? Now reactant A is the analyte. That's the one that we're trying to figure out the unknown concentration of. The reactant B is the one that we know the concentration of and the volume. So that's the standard solution essentially. So you perform that titration and there's a reaction that occurs, okay? Now the second step of this is the remaining excess reagent, so the leftover from the first reaction of reactant B, because we're going to put excess in there, more than what we need, okay? And that's going to be, that leftover, undergoing a secondary reaction with a differing reagent. So you're now going to have a second titration where you've got reactant C reacting with reactant B, okay? And essentially what we do is we figure out the excess of reactant B, okay? So we figure out how much was left over, and then we subtract that from the original amount of reactant B, okay? So the original amount that we have, and the difference between those two will be the amount that reacted with A, so we can then work backwards in order to figure out our reactant A, okay? So this might be used if the initial reactant is unable to be determined via a primary titration, okay? So if it's more difficult, then we need to do this two-step analytical technique. Now, in terms of the difference of a worked example or a practice problem, there's literally one extra step. It's a subtraction step, okay? But the difficult part is you'll get given two equations because you have the reaction 1, so the primary reaction, and then you have the secondary reaction with the excess from, or the leftover, I guess, from that original reaction, okay? So you're gonna have two equations to work with. Now, if the question is asking you for the reactant in excess, then you're basically looking at this one here, the second equation, okay? And then you'll work backwards to figure out the equation 1. So realistically, you're gonna start looking at equation 2 first when you do the practice problem, and then you'll be looking at the initial equation 1, okay? So let's look at the practice problem here. So we've got the concentration of carbon dioxide, CO2 in air can be determined through an acid-base back titration. A 3.5 litre sample of air was bubbled through a 50 ml sample of a 0.0200 mole per litre barium hydroxide, precipitating barium carbonate. So essentially, carbon dioxide was reacted with the barium hydroxide, and the excess barium hydroxide, what was left over, was titrated with hydrochloric acid. So this here is going to give us the information that we need to start, okay? So the excess was titrated with this concentration of HCl, and the average titer of the chemical was reached, okay? So the first step is you want to calculate the original number of moles of barium hydroxide from the volume and the concentration supplied prior to the reaction, and label the quantity as the original. So see here, you had given the volume and the concentration of the original barium hydroxide. So we have number of moles, concentration times volume, and we make sure we label this as original. So this is going to come into play later, okay? So that's the original number of moles up here. Second, we'll determine the quantities working back from equation 2 to equation 1. So we calculate the known number of moles of hydrochloric acid by using the average volume of the concordant titers and the concentration of the aqueous HCl. So essentially we're working out the number of moles of HCl, which is the concentration of 0.0316 times by the volume. Now remember, for a titer value, volume is usually in mil, but we need to convert that to liters. So that's going to be divided by 1,000. So we get this many moles here, okay? And now we're going to use our mole ratio in order to determine the number of moles of the excess barium hydroxide, okay? So note that when this is actually used here, it says excess, okay? So that's different than the original that we had previously. So the amount in excess, so you multiply by the mole ratio, which is the number of moles of unknown over known. So in this case, it's going to be the unknown, which is the, let me look at this quickly. So the number of moles of unknown, which is the barium hydroxide, so 1, divided by the number of moles of known, which is the HCl. So essentially, you multiply by half. So essentially, this answer here is half of this previous answer here. And that gives us the number of moles of the excess barium hydroxide. Next is going to be the subtraction step. This is the step that's unique to the back titration. So this will link the first equation from the second equation. So what we do is, in order to get the barium hydroxide that reacted in the first equation, we need to subtract the original, so everything that we put in at the start, subtract the excess. So you always do this subtraction step for a back titration, okay? And essentially, it always follows the same pattern. And what I mean by that is, in this question, it's always broken down in the same format. So for part D or part 4, you're always going to get answer from step 1, subtract answer from step 3, or answer from part A, subtract answer from part C. So that's essentially all you need to do. So the reacted is answer from part A, take answer from part C, gives you that new step 4. So that new number of moles reacted. Then we essentially do the same thing again. So mole ratio, in order to connect the reacting barium hydroxide to the reacting carbon dioxide. So 1 to 1, so it's going to be the same answer. Okay. Remember, always label number of moles of CO2, so label what you're doing. And then calculate the concentration of carbon dioxide in moles per litre. So we convert that into a concentration, number of moles divided by volume, gives you that molar concentration there. Now convert molar concentration to ppm, so that would be 2 steps. Molar concentration to mass concentration is multiplied by molar mass of the carbon dioxide, which is the 44.01. And then from grams per litre to milligrams per litre, we multiply by 1,000 because there's 1,000 milligrams in a gram. And the knowledge that milligrams per litre is the same thing as parts per million, or ppm. So that gives us our answer here. So having said that, let's try the practice problem. So aluminium sulfate can be added to domestic water supplies as a coagulant or a flocculant. So essentially what that means is it congeals these fine particles together so they can be removed via filtration. To remove fine clay particles, by using a back titration with EDTA and a suitable indicator, the concentration of aluminium ions can be determined. A 25 ml sample of water was transferred to a volumetric flask along with the 30 ml of the 0.010 mole per litre EDTA. And here's the equation. Now this might be a little bit confronting because you're not really sure what EDTA is. Now it is a coagulant and this is the equation. It doesn't really matter if you're not really sure what it means. We're just going to follow the same process, okay? So calculate the original number of moles of the EDTA. Okay, so the number of moles of the EDTA, so that's this and this. So we're just going to have number of moles of the EDTA is equal to concentration times volume, which is equal to the 0.010 multiplied by the volume. So 30 ml becomes 0.03 litres, which is going to be 0.01. Oops. Yep. 1 times 0.03 is 3 times 10 to the negative 4. Mole. Okay, and that's it for part 1. So for part B, calculate the number of moles of the zinc ions that reacted with the excess EDTA. So we'll just need to flick back, and the zinc ions here. So I missed a part of the question here. So the excess EDTA was titrated with 0.0010 mole per litre zinc sulfate, and we had the concordatize below. So calculate the number of moles of zinc ions that reacted with the excess EDTA. So the EDTA with the zinc sulfates, and we need to calculate concordant titers here. So essentially, concordant titers are within 0.1 mil of each other. Now these are not concordant, however, they're all kind of included here. So I would just be averaging all of these out. So that would average out to be 52.8. But realistically, I know that concordant titers are within 0.1 mil. So realistically, it should either be the average of these two or the average of these two. It shouldn't be all three. So I think, to be honest, that's a bit of a mistake in the essentials, but that's okay. We'll just go with this. So 52.80, I apologize for that. So the number of moles of the zinc ions is going to be concentration times volume, which is the 0.001. Multiplied by the 52.8. Now we're going to turn that into litres once again. So that's 0.0528. 0.0528 times point. So I got too many things open here. Okay, I just kept writing a little bit, but so it's 0.0528, which is going to be 5.28 times 10 to the negative 5 mole. So the next one is calculate the moles of the excess EDTA. So the excess EDTA is essentially this amount here, okay? And it says in the question that this is the excess that you're looking at. So what we're going to do here, this is a mole ratio question. So I'm going to say the number of moles of the EDTA in excess is equal to the number of moles of the zinc ions, which is what we just calculated up here for part 1. And the reasoning is because it's a 1-to-1 mole ratio. So if we look at this equation, it's 1 of these versus 1 mole of these. Okay, so it's the same answer. However, if it was a different mole ratio, let's say, for example, there was a 2 here and a 1 here, that would be multiplied by the mole ratio, which is unknown over known. Okay, but because it's 1 and 1, we don't really need to do that step. So the next part is the subtraction. So how many moles of EDTA that reacted with the aluminium ions? So if we go back, this is the number of moles, this is the EDTA that reacted with the aluminium. Okay. Now what we have over here, and I didn't write this before, I probably should have, is this is the EDTA original, or the OG. So that's what we added in originally. Okay. And then a certain amount reacted in this first one. That's what we're trying to figure out. So in order to calculate the EDTA that's reacted, we need to take the OG EDTA from the first part, subtract the EDTA in excess, and that's this one here. So we do that subtraction, and this is where I made a silly mistake. So I need to completely get rid of that because that's embarrassing. So 3 times 10 to the negative 4, and I've just got it here, 3 times 10 to the negative 4, subtract 5.28 times 10 to the negative 5, gives 2.472 times 10 to the negative 4. Okay, so I don't have much room here. I'm just gonna, actually I'll write it here. 2.7, oh sorry, 47, 2.47. Oh, that's horrible. I'm gonna do it up here. 2.47 times 10 to the power of negative 4 mole. Okay, so that's the EDTA that's reacted. So hence calculate the concentration in mole per litre of the EDTA, of the aluminium ions present in the water sample. Okay, so first of all, we need the number of moles of aluminium in order to calculate the concentration. So let's go back to the original equation. It's a 1-to-1 ratio again. So 1 of these and 1 of these. So essentially, the number of moles of aluminium is the same thing as the number of moles of the reacted EDTA, which is that there. Okay, so we can just say the number of moles of the aluminium ions is equal to the number of moles of the EDTA that have reacted. Which is because of a 1-to-1 mole ratio. So that's equal to the 2.47. Oops. Times 10 to the negative 4. Then the second step is concentration is equal to number of moles divided by volume. So that's 2.47 times 10 to the power of negative 4 divided by the volume of the water sample. Now from memory that was 25 mil. Yep, 25 mil sample of water. So that's going to be 0.025 litres of water. So remember we keep that answer in the calculator because I rounded it off here. So we keep the whole number there to make it more accurate. And we just go answer divided by 0.025 is 9.89 times 10 to the negative 3. Moles per litre. Okay. And express the concentration in ppm present in the water sample. Now, what we want to do is we want to go from moles per litre to grams per litre, okay, which is multiplied by molar mass. And then from grams per litre, we want to go to milligrams per litre, which is per litre, so from grams to milligrams is times by 1,000. So that's a two-step unit conversion there, okay? So, and milligrams per litre is equal to ppm, because ppm is milligrams per litre. You just essentially have to remember this stuff, to be honest. Like, I remember milligrams per litre is ppm. I know that there's 1,000 milligrams in a gram, so that's how you go from there to there. And I know that the molar to mass concentration unit is either times or divided by molar mass, depending on which way you go. So that it's just something that you get better at with practice and that you remember with practice. Okay, so I'm just going to do it in the calculator. This times by the molar mass of aluminium. Now, you'd have to look up aluminium on the periodic table for this. Now, aluminium is 26.98. Okay, the mass number. I couldn't remember that off the top of my head. So we just go that times 26.98, and then we times by 1,000. So our answer is, now I should write all this down, but I'm just going to shortcut it, 266 or maybe 267 ppm. Oops, ppm. Okay, and that's it. So that's your back titration problem, completely sorted. Thanks for watching. Hopefully that helped a little bit. Go back, have a look, ask me follow-up questions if you need. Thanks.